Hello my dear students, in this lecture we are going to see fatigue design under combined loading or complex loading. We can say complex loading also. Let us say, my dear students, the stress tensor at any point is given like it is written in the form of matrix that already we have defined in basics, right? And it is written like sigma x, tau xy, tau xz, tau yx, sigma y, tau yz, then tau zx, tau zy, tau zy, it is tau zy, and sigma z. This is the 3D stress tensor. Now let us say component subjected to three-dimensional loading on which there are normal stresses also and shear stresses also. Then for such a type of problem we have to find equivalent stress. Now again it is fluctuating stress. This stress tensor is fluctuating continuously. The loading is fluctuating from maximum to minimum values for respective stresses, right? Now for solving such problems we are using distortion energy theory. For solving such problems we are using distortion energy theory, and as per distortion energy theory, the equivalent stress, that is sigma equivalent square, is equal to this formula we have derived in theories of failure. you go in you go back in theories of failure topics, you will find this derivation. Sigma equivalent square is equal to 1 by 2 in bracket sigma x minus sigma y whole square plus sigma y minus sigma z whole square plus sigma z minus sigma x whole square plus 6 tau xy square plus tau yz square plus tau zx square. This is the formula. This is the formula derived as per distortion energy theory to find equivalent stress, and sigma equivalent is equivalent effect of all the stresses together, right? It is also called equivalent stress. Now for such type of loading we have to see how to design the component. Now we will see special cases, that is case 1, that is 2D loading. For our syllabus we have 2D loading here. For our syllabus in this topic we have 2D loading. Now we will see the special cases on 2D loading, right? Then first special case is here. The first special case is case 1, when a component subjected to only normal stresses along two direction. Case 1, only 2D loading, without shear, and tau xy is equal to 0 without shear. That means a component subjected to, let us say, a component subjected to sigma x normal stress along x direction and sigma y, that is normal stress along y direction and normal stress along x direction. Means in this loading can we say sigma z is 0 as well as tau xy as well as tau xz as well as tau yz, all are 0. Now use the distortion energy theory and find sigma equivalent square, which was 1 half in bracket sigma x minus sigma y whole square plus sigma y minus sigma z whole square plus sigma z minus sigma x whole square plus 6 tau xy square plus tau yz square plus tau zx square. This was the formula to find sigma equivalent. Now here all the shear stresses are 0, means this term becomes 0. Then sigma z is 0, put all the values over here. Therefore sigma equivalent square is equal to 1 half in bracket. Now it is sigma x minus sigma y whole square plus sigma y square plus sigma x square, right? Now simplify this. Therefore sigma equivalent square is equal to 1 half in bracket. Simplify this bracket. Therefore sigma x square minus 2 sigma x sigma y plus sigma y square plus sigma y square plus sigma x square. This will be the simplification. Again simplify this. Therefore sigma equivalent square is equal to 1 half, here sigma x square 2 sigma x square sigma y square plus 2 sigma y square minus 2 sigma x sigma y. Now if I take 2 common, what will be there? Sigma equivalent square is equal to 1 half into 2 sigma x square plus sigma y square minus sigma x sigma y. Therefore 2 will get cancelled. and the equivalent stress will become under root of sigma x square plus sigma y square minus sigma x sigma y. This formula is very important, and this result we have already seen. This is the distortion energy theory only. This is a distortion energy theory formula. Therefore, for 2D loading having only normal stresses, the sigma equivalent stress is under root of sigma x square plus sigma y square minus sigma x sigma y. This formula we have to use. Now, again this stress is fluctuating. This is fluctuating stress or not, means sigma x is fluctuating from minimum value to maximum value, as well as sigma y is fluctuating from minimum value to maximum value. Therefore, for such type of loading, we have to find mean stress and stress amplitude. Therefore, if I want to find mean stress, then is equal to under root of sigma x mean square plus sigma y mean square minus sigma x mean sigma y mean. We have to consider all the mean values, right? And stress amplitude is equal to under root of sigma x amplitude square plus sigma y amplitude square minus sigma x amplitude into sigma y amplitude. This is how we have to solve. And what is mean stress? Mean stress is maximum stress plus minimum stress divided by 2, and amplitude stress is maximum stress minus minimum stress divided by 2. This is the stress amplitude. This is how we have to convert, this is how we have to find equivalent stress, and then proceed with by helping with the help of stress amplitude and mean stress. Then use either any diagram, that is Soderberg diagram or Goodman line or Gerber parabola or modified Goodman diagram, as per question requirement. Solve the question. And let us say case 2, this was the first case, that is it is subjected to normal stresses along both axes. Now let us say the component is subjected to combined bending and twisting. Second case is the component is subjected to 2D loading. In 2D loading, combined bending component is subjected to combined bending moment and twisting moment and twisting moment, right? Now again in theories of failure topic we have seen this. For combined bending and twisting moment, in component there is bending stress, let us say there is a bending stress sigma b, right? As well as there is torsional shear stress due to torque. Due to bending moment there is bending stress sigma b, due to bending moment there is bending stress sigma b, and due to torsion there is torsional shear stress tau. As per the formula, m by I is equal to sigma b by y. From this formula you will get bending stress sigma b is equal to m by I into y. For circular shaft we have derived this formula as 32 m upon pi d cube for circular shaft, and from torsional equation, that is T by J is equal to tau by R. Therefore we will get torsional shear stress is equal to T by J into R. And for circular shaft we have derived this formula as 16T upon pi d cube. If you don't know these formulas, you can go in theories of failure topic to watch this formula or derivation of these formulas, right? Now here we are deriving combined bending and twisting moment, the formula for combined bending and twisting moment. Now here in this equation can we say, sigma x is equal to sigma b and tau xy is equal to tau. But here sigma y is 0, sigma z is 0, tau yz is 0, as well as tau zx is 0. These all terms are 0. Now put the variable formula, that is sigma equivalent square is equal to 1 half, the formula is 1 half in bracket sigma x minus sigma y whole square plus sigma y minus sigma z whole square plus sigma z minus sigma x whole square plus 6 tau xy square plus tau yz square plus tau zx square. Apply this formula. Now put the values. Therefore sigma equivalent square is equal to 1 half. Here sigma x is only present, therefore sigma x square, therefore this term will become 0 totally, plus sigma x square plus 6 tau xy square plus 6 tau xy square, right? Therefore what the formula will become? Sigma equivalent square is equal to 1 half 2 sigma x square plus 6 tau xy square. Now simplify this. Therefore sigma equivalent square is equal to 1 half, if I take 2 common, then in bracket sigma x square plus 3 tau xy square, right? Therefore 2 will get cancelled, and from this I will get sigma equivalent is equal to under root of sigma x square plus 3 tau xy square, right? This will be the for combined bending and twisting moment. Now therefore the equivalent stress sigma as per distortion energy theory for combined bending and twisting is under root of sigma b square, sigma x is bending stress, plus 3 tau square, tau is torsional shear stress. Now if I want to find mean stress, this is equal to under root of sigma b mean square plus 3 tau mean square, right? And if I want to find stress amplitude, then I have to consider bending stress amplitude and torsional shear stress amplitude, that is sigma b amplitude square plus 3 tau amplitude square. These formulas we have to use, and as per different diagrams we have to go for design, right? Now very important note in this topic is, by inducing residual compressive stresses, fatigue strength is increased because the effect of discontinuity is decreased by compression. Now to understand this note, let us say one component is there, let us say this is a component and there is a notch on this component. Let us say there is a notch on this component, right? Like this, there is a notch on this component, and this notch is nothing but discontinuity. This is a discontinuity, right? Here there is a discontinuity. Now on this component, if I apply compressive stresses, initial compression, it is called initial compressive stresses, let us say this compressive stress is applied. Because of this initial compression, the fatigue strength is going to increase. This is the statement. See, because of this compression, can I say the notch is going to decrease? Because of this compression, the notch will decrease, the notch will decrease, and as notch is decreasing, the notch is decreasing, therefore strength is increasing, means discontinuity is decreasing, hence strength of component is increasing. But instead of applying compressive stresses, let us say on this component if I apply tensile stress, on this component if I apply tensile stress, right? For this tensile stress, instead of decreasing notch, the notch will increase. Instead of decreasing notch, the notch will increase, and as notch increases, strength definitely decreases. Means if I apply residual compression, means initial compression before loading, initially we are compressing the component so that the fatigue strength is going to increase. Thank you dear students. In next lecture we will see numericals on this topic.